Hi everyone, welcome to Liquid Brain. In this video, I'm going to share with you what is Log2 function and try to understand differential expression analysis by DESeq2. So when we deal with high throughput omic data, we normally will do this step, which is the differential expression analysis, and here's the result. Definitely, we will look into the log2 fold change value to check the changes in the gene expression, and also we might filter the gene based on the p-value, but normally we will know that instead of p-value, we will go for p-adjusted value. And also, there's the condition that referring to this differential expression analysis, but you're aware of this and do you put the correct factor? So there's a lot of why in my brain. So there's always things for me to confuse whenever I look into this result, what is the log2 fold change, why we don't strictly use fold change, and how DESeq2 able to do this thing, and also how can I reproduce the result using DESeq2 R script. Okay, so first of all, what is fold change? So here we have two groups, group A and group B. In order to compare them, the most straightforward way is to get their ratio. So the ratio is like the value of A divided by the value of B. So for example, the fold change of A versus B is 2/1, which is 2, and then the fold change for B versus A will be in the reverse way. So the same things go for the others. Here, maybe we just pick the first row to see. So the fold change of A versus B will be 2, and then fold change of B versus A will be 0.5. So we can see that there is a twofold increase in the case of A versus B, but there is a 0.5-fold increase in the B versus A. So this actually created a certain type of the confusion, what 0.5 means and what is like twofold means. But in fact, they are referring to the same set of the comparison. When there is the condition where both of the sample having the similar result, let's say each of them have 1, so the fold change will become 1. And this actually another confusion, which is means one fold change means no change. So they create a lot of the confusion when you just use the fold change directly. That's why here comes to the way to use logarithm based 2 transformation, which means that we convert the value into the base of 2 and then we log2 transform them. So here's the example. There's a condition where A versus B, which is 2/1, which we will have 2. Log2 fold change of 2 is 1. For the reverse way, where is the 1/2, it will become 0.5. And 0.5 log2 then will become -1. So this is something that the logarithm based 2 transformation is the way that where we want to take the exponent of the power of 2. Let's see the value in the figures. So we will have something like this. When we compare A versus B, that 1, and when compare B versus A, that also be 1. So it means that the treating increasing and decreasing ratio in a similar manner. When they come to the situation where both samples having similar value, the log2 function will be just 0. So this means that we can easily understand that log2 function 0 equal to no changes. How about the condition when one sample having certain value but not expressed in the other sample? Log2 fold change will just not able to do it, just couldn't interpret this. So this also is good whenever we want to do something like fold change study, because it will eliminate those genes or items that not expressed in the other sample. Another benefit is the log2 fold change way will be a better way to eliminate the effect of the outlier. For example, comparing the mean of the fold change and the log2 fold change. For the fold change, we will get something like maybe 3.667, and the log2 fold change maybe we will get something like 1.333. So we can see that the value of the log2 fold change mean is closer to the mean of what we expected, which is like the replicate to the mirror value, which means that the outlier will have less effect on the geometric mean, and this is also what we mean by the mean of logs. So a little bit recap here. Log2 fold change transformation is good for symmetrical and linear relationship of the differences. This leads us that very easy to understand the relationship of the numbers. And then this is the better unit for fold change study. And also geometric mean is less sensitive to the outlier. So let's have a look on the differential expression analysis in the omics study to understand log2 fold change better. And when we deal with a lot of the data, and what I mean here is 10 or 100,000 or even million of the data in omics study, there's always the challenges when we want to analyze them. It is because they're always having certain type of the variation that affecting their true value. So for example, the two most well recognized variation is the library size and the library composition. For the library size variation, let's say both of the sample A and B are the same object. However, the sequencing for the sample A is just gone through 12 reads, which means it's only shallowly sequenced. Whereas for sample B, it has a much better sequencing depth, which is 3-fold increase of the sequencing reach. So it will have slightly more of the sequencing rate compared to sample A. And the other one is the library composition variation. So for example, in the sample A and B, both of them have the similar expression for gene 1, 2, 3. However, for gene 4, they only present in sample A but not in sample B. So when they go through the similar sequencing depth, let's say there's the 90 reads, because the condition B does not having gene 4, 90 reads are all distributed evenly to the genes 1, 2, 3. While we can see that is the uneven distribution between condition A and B, the original real expression level of gene 1, 2, 3 are in fact the same. So this is not really fair when we want to compare them. That's why we need to do something to adjust the expression level so that the effect of this variation will be reduced. So what we normally do is to convert the data into the TPM or FPKM so that we can compare them, or we can use the statistical approach to identify the differences between two samples. So the most commonly used statistical model is DESeq2. From the user end, it is pretty simple. We just need to run 2 lines of the R script to get it done. So first is like to input the data, and secondly run it. And I will talk about this at the last part of the video. But first, maybe let's try to understand the theory behind DESeq2. So assuming we want to compare the gene in group A versus B, and it is like quite straightforward. We just get the log2 fold change value to see whether the log2 fold change between the group is 0 or not. If let's say it's 0, that means there's no difference between these two genes. But if let's say there's more than 0 or less than 0, that means the it's having something differences between them. So this is the thing. We want to make the null hypothesis that if let's say in the normal condition, the log2 fold change is normally 0. So now we try to see how we actually investigate it. First, we need to know the accurate read count for this gene value, because have you known earlier, the gene expression value that's shown in the sequencing result, this is not the real value of the sample. It's kind of biased by the technical variation. So at first, we need to eliminate the technical variation. Okay, so now there's 2 tasks for DESeq that I want to do. First is like to get the accurate read count, and secondly compare the log2 fold change value to see is it enough to reject the null hypothesis. Okay, so this is the formula for the DESeq2 to estimate the read count of the gene. So this is a bit complicated, but their logic can be understood. So I hope that you could bear a few minutes and try to explore with me. In order to estimate the read count, DESeq2 need 2 elements, which is the first is the mean of the read count. and secondly, the dispersion. And for the mean here, there's come with the formula like this. Again, it needs two elements. The first is the Q here. Q is the parameter obtained from the raw count of the dataset, which is something that we fit into the model. Secondly is the size factor. So size factor is something similar to the normalization factor. In order to obtain the size factor, first we need to convert the value into the log2 value. From there, we obtain the geometric mean, which is the average of the log mean, as seen here. And after that, we get the ratio of the sample referring to the pseudo mean. From the list of the ratio, we can get the median of the sample. DESeq2 use median instead of mean is also a way to eliminate the effect of the outlier. So from here we can see that there's number, like let's say this is 0.7x61. This is the value after log2 transform. So before we want to convert it into the size factor, we need to convert it into the normal value, and then it will become the size factor, which is 0.277 for sample A. And from here we can obtain the normalized count by dividing the original count over the size factor, and that's all. We can get the size factor and also be able to estimate the mean count. So this step able to eliminate the variance of library size as well as RNA library composition. So let's move to the next element that the model needs, which is the dispersion. Normally in negative binomial, we need two things, which is the mean and also the variance. But for DESeq2, they don't use the variance directly for a reason. So what is variance? This is something that differs among the sample. Let's say for genes 1, the variance is something that, let's say, 0.2. The variance is the differences of the value from the mean. And let's try to plot the variance count versus mean count. We will get something like this. So when we try to plot the omic data, which is high throughput data, normally we will obtain something like this, which means that a lot of the samples are with low mean and also with low variance. However, there are less genes that having high mean count and also high variance, which is something like this. So from here we can see that variance is directly correlated with gene expression level. And this is not what we want, because to get the differential expression gene, we assume that there should be something with higher mean count. We don't want to come up with a lot of the data with low mean count. And again, we try to see the formula. Alpha here is referred to the dispersion, and we can see that this is directly correlated with variance, which means that increase of the variance is also increase of the dispersion. While for the mean here, there is the something different. Decrease of mean will lead to increase of the variance. From here we can get the dispersion versus mean graph like this, in a way that they put more weight for the genes with the high mean count and low variance. So maybe we study a bit of this dispersion. So this is what the DESeq2 model get the individual dispersion estimate. And using this dispersion estimates, we can fit the curve like this. And now is the thing, this independent dispersion estimate come from the replicate of the sample. Let's say we do maybe 2 to 3 replicates for per sample, which is not enough power when we want to fit the curve. So DESeq2 do in a way that they try to get the gene-wise estimate, which means that the gene with similar average mean will have the same dispersion estimates. And from that, they also try to screen the estimate. As we can see from the figures, the dispersion estimates are stronger toward the fitted curve. However, those dispersion estimates that too far away from the curve and above of the curve will not be shrunken. This is to avoid the false positive that happen, because they're most likely not well fit for the model. So the blue bubbles here are those dispersion estimates that not going to fit into this model. So this is how we interpret the graph, and now DESeq2 has gotten the good fitted model for the rate count. So they can proceed to the next step, that to test the hypothesis by word test. And this read count will be treated as the real gene value of the samples. And then from there we can obtain the coefficient beta, which is the log2 fold change. And finally, DESeq2 able to test the hypothesis by word test by default. The null hypothesis is the coefficient is lower than the theta threshold, which is 0. In the layman word, it means log2 fold change is equal to 0. So a recap of the DESeq2 model. The first two steps is to estimate the two elements that required for the negative binomial model. This is to normalize the sample value to make them comparable. And lastly, DESeq2 use this to fit the negative binomial model and test if the gene is significantly different by using the statistical test. So now maybe we go back to the user end of the DESeq2 analysis. As I mentioned earlier, this just requires two simple steps to run it. The first is to create the DESeq2 model. Here, this is the data set from matrix. Cow data refer to the gene expression matrix file, and the row refer to the gene, and the column refer to the sample. And the core data is the metadata, also called as the sample information. And here they listed two information, the condition and the type. The design is the factor that you want to compare, and here this is just single factor, which is the type. After that, we can just run DESeq2, and this step is where DESeq2 run to get the size factor, the dispersion, and to fit the model, and lastly to compare them using the statistical test. So from here, we can check the result, which is something like this, as I mentioned in the beginning of the video. So let's look closer to interpret DESeq2 result. At this moment, I hope that you already understand why we need to use log2 fold change here. And if let's say you want to know better of what these things refer to, you can try to run the code mcode description. So from here, we can see that the first is the base mean, which is the mean of normalized count for all samples. Secondly is the log2 fold change, and this is the standard error, and that refer to the statistical test that you choose. By default, this is the word test. They show also the condition that you choose for the design. And then the p-value refer to the word test p-value. And here we have to know that p-value here means that it's the test for individual genes. When we make it into the multiple gene comparison, we have to use the adjusted p-value, which is that already collected by the Benjamin Hochberg statistical analysis. So that's why we don't use p-value but adjusted p-value to see whether we should reject the null hypothesis. In summary, log2 function more than 0 means the gene is upregulated, and when it is equal to 0 means the gene is kind of like no change and irrelevant to the study. And when the log2 function is less than 0, the gene is downregulated. Okay, so in R, there's a lot more things we can customize using these two packages. So the first thing is we can change the type of the input. Just now, what I demonstrated is a metric file. This is also can come from other data input, which is from the transcript abundance files, from high-seq count file, or from a summarized experiment object. The other thing is the design, which means instead of the single factor design, we also can apply multi-factor design or with interaction, which is something more complicated. And if let's say we use the multi-factor design, we can try to check the result based on the specific group comparison. And also you can choose another type of hypothesis test with the LRT, likelihood ratio test. The null hypothesis of LRT is comparing two models. The full model fits just as well as the reduced model, which means this is more suitable for the multi-factor design. And as a reminder, word test is to test the null hypothesis of one single model, which is within the model, the log2 function is equal to 0 or not. And next, they also have some other stringish approach for better visualization. And this is another part of DESeq2 that might take some time to explore. So now's the thing, you already obtained the DESeq2 result, and you don't really just go for the log2 full change. In fact, you still can use the log2 full change result to go for some downstream analysis. For example, gene set enrichment analysis, or the other type of the visualization using heat map, PCR, or so on. So a little bit recap of the video today. Fold change is the ratio of the samples, and log2 fold change is a better way to study the fold change because this is easier for us to understand. DESeq2 model is very perfect to normalize the data, fit the model, run statistical analysis to identify differential expressed genes. From there, they already kind of take care of all the unwanted variations which exist in the sample. And also we can easily use DESeq2 package in R, and there's room for customization. So that's all for my sharing today. I hope you learned something from this video. Thanks for watching, and I'll see you next time.